Hello students, today I am going to teach you 7th unit of control system, that is concept of stability and algebraic criteria. Okay, so the concept of stability is one of the most important subject in control systems. Okay, so here stability is the most crucial problem in the design of control systems. So we see the learning objectives of this unit. Okay. So at the end of this unit, you will be able to understand the concept of stability, and you will be able to find stability of the system. Okay. So this is two learning objectives. Is end of this lesson you are able to understand the concept of stability and to find the stability of the system. As I said before, okay, stability is the most crucial problem in the design of control system. After you design any system, so we must know the stability of the system. If a system become unstable, it will be thrown out. It will not be useful if a system is not stable. Okay, so now we see what is the stability. What is stability? What is stability? What is stability? So stability says that, so for bounded input, if you get the bounded output, so that is called BABO stability. It means if we give bounded input to the system, see if this is a system, if it is a system, a control system, okay, if input is bounded, bounded input is bounded, so if we give bounded input, so you will get bounded output, right? If we give unbound input, okay, you may get unbounded output. So first we have to give bounded input to the system, so your system will get the bounded output. So we say this is a stability. This is stability. We see some other definitions also, similar definitions. Stability means it measures of the tendency of a system's response to return to zero after being disturbed. Let's just see that I am writing another definition here. Stability. So a measure of the tendency of a system's response to return to zero after being disturbed. What does stability means? A measure of the tendency of a system response to return to zero after being disturbed. It means when the system is disturbed, it should return to its normal position. So if it is not happen, so we say that is unstable system. If you just take a system which consists of small ball, you take this system, and I'm going to take this system which consists of a small ball, here. This is a ball. Okay, so this is a ball. Okay, so and this ball is initially at rest, the equilibrium position. This ball is initially at rest and equilibrium position. Okay, when the ball is disturbed, the ball started to oscillate. So it means when the ball is disturbed, so it means when some force is applied on this ball, what happened? So this ball is disturbed. Okay, so it start to oscillate. The ball is start to oscillate. Okay, so what happened? Eventually, the friction is eventually come be to rest back out equilibrium position. So that is stable. So what happened after sometimes when you apply force on this, what happened? This ball will oscillate. So the friction eventually come to rest back at equilibrium position. This is a stable system. Okay, if you just see that, I'm just going to draw the graph. So this is a T. So when you apply some force on the ball, so it will oscillate and finally it will come to rest and equilibrium position. So it will oscillate like this. So finally it will come to rest and equilibrium position. So if I take if I take another system, so this is a mountain. So I call it this one is a mountain. So on the top of the mountain, I put a ball. On the top of mountain, so I placed a ball here. So this is a ball. So now see that this ball is at rest position and equilibrium position. Okay, so the ball is placed top of the mountain and I'm going to perform the same experiment which I performed before. Okay, so not what I'm going to do now. So since the ball is here in equilibrium position or right position, I am going to apply some force on this ball. Okay, when I applied on the force on this ball, so when I disturb this ball, what happened? It rolls down. It never come back to its original position. It never come back to equilibrium position. Never come back to at rest position. So this is called unstable system. If you just see the graph, here, so this time will go in infinity. This time is infinity. This never come back to its original position. So this is one of the simple example for the stability of the system. Okay, so even we see that some other examples also. If I take any system, see, if you take any system here, okay, if we give a bounded input, if we don't get bounded output, the system is unstable. Okay, we see now mathematically we will find stability of the system. So what is the stability? Stability means for bounded input and you will get the bounded output. Okay, the input should be bounded and you should get the bounded output. Then we say system is stable. Okay, so mathematically we see that mathematically, so we know that y of s is equal to b0 s power n plus b1 s n minus 1 plus b2 s n minus 2 plus bn by so a naught s power n plus a1 so s power n minus 1 plus a2 s power n minus 2 plus so on so a n. So this is a transfer function. So here this one is called characteristic equation. This equation is called characteristic equation. So generally we write C in short form. So characteristic equation. So the characteristic equation is a naught. So I am going to write here characteristic equation a naught s power n plus a1 s power n minus 1 plus a2 s power n minus 2 plus on an is equal to 0. So this is a characteristic equation, very important equation. Okay, so this characteristic equation has the poles of transfer function. I mean here you see that this if I can write this as a in the form of partial fraction expansion. I can convert this in the form of partial fraction expansion. When you convert this, so this is y of s is equal to k into system gain s plus z1, okay, s plus z2, so s plus z3 and so on by s plus p1, okay, s plus p2, s plus p3 and so on. So this means so this transfer function has a poles of transfer function and also okay, this characteristic is the poles of the transfer function. So after we converting this into partial fraction expansion, so here z1, z2, z3 actually we call it zeros of transfer function. Okay, here p1 comma p2 and p3 we call it poles of transfer function. K is system gain. Okay, here zeros of the transfer function change the magnitude of the response and will not change the character of the response. So these zeros, the z1, z2 to only change the magnitude of the response and will not change the character of the response. Okay, so the character of the response, whether stable or unstable, constant, growing or decaying, will be given by the roots of the characteristic equation. So the characteristic of the response will be given roots of the equation, roots of the characteristic equation. It means p1, p2, p3 will give the correct response system. It will determine the response. So that is very important to remember. I'm going to show you the few important things here, very important things. So if you take here you see that if I take I'm going to take S plane. So this is called S plane. I'm going to scan this S plane. This is zeta, this is j omega. Okay, so if a pole is at this place, if the pole is the negative real axis, if the pole is like located at this point, so you will get decaying response. So this is a stable system. So if your roots are complex conjugate, okay, so if your roots are located on the complex plane, so you will get this kind of response. So is a exponentially decaying response. So you see that you will get this kind of response. So this is a stable system. Okay, so in another situation, if we get the roots real and equal, the roots are real and equal, so you will get this kind of response. For roots are real and equal, so you will have this kind of response. Whatever the system become stable. Here also, see, if the poles whether real, here the poles are real, whether it is a real or complex, distinct, repeated, any way they appear. Okay, if the poles lie in the left, the poles lie in this particular region, in this particular case, it is guarantee that the necessary and sufficient condition which we have established for stability is always satisfied, therefore the system is stable. It means here, for stable system, the poles will lie left half of the S plane. Okay, so these poles are not lying this right side of the S plane. This is called right half of S plane, this is left half of S plane, this portion. So this portion is right half of the S plane. When you observe for the stable system, all the poles are lying at the left half of the S plane. So the system, we call it a stable system. So now look at the right hand side. So now look at the right hand side, means right half of the S plane. If you see right half of the S plane, I take a graph here. So I just going to scan this S plane. So if you just see that if a root is located at this point, so what happened, you will get growing response. Actually this is an unstable system. Okay, if the roots are complex conjugate, here is one root, this is a complex conjugate, so you will get exponentially growing response. So exponentially growing response, this is exponentially growing response. So it is not going to be stable, it's not going to be stable system. This is a unstable system. So this system is unstable system. It means, so you see that all the poles, when you observe this, all the poles are lying right above the S plane. So the system is unstable. So the condition of stability is all the poles in left above the S plane. What is the condition here? The condition for stability. So the condition of stability is all the poles in the left half of S plane. So what this is the right side. Okay, this is the right side. So here so what happened, for instability system, system, at least one root in the right half of S plane. Okay, so if we see that in this case, what happened, the system is instability. What happened, what again I'm telling, unstable unstability definition. If all the roots lie right above the S plane, but one pole is lying on the right of the S plane, so in that particular case the system is unstable. The system is unstable. Now we have seen right above the S plane and left above the S plane. Now we see the poles locating at on the imaginary axis. So on imaginary axis I am going to take it. Okay, so in this situation, suppose I am going to draw this S plane. This is a S plane. I am going to draw. If a pole is at origin, if a pole is at origin, so if a pole is at origin, you will get this kind of response. So this is an unstable system. If a simple if a pole pair at the origin, so you will get oscillatory response. So the simple pole pair, so what happen, you will get this kind of response, oscillations. So this leads to unstable system. And also if a pole pair on the imaginary axis, the pole pair, here is one pole pair and here is another pole pair, so what happen, it will give growing sinusoidal response. It will give growing sinusoidal response. If we just see that, so so it will give growing sinusoidal response. So see, it's not going to stable. So this is going, this is growing response. So this never become stable. This is an unstable system. You see that I am going to revise. So first, if a pole is at origin, so you will get this kind of response. This is unstable system. Okay, if a simple pole poles on the imaginary axis, you will get oscillatory response. This will lead to instability. If a pole pair on the imaginary axis, so you will get growing sinusoidal response. So this is exponential. This is a growing sinusoidal. This is unstable system. Okay, this is unstable. So the basic definition in this particular, it is seen whether a single pole or a single pole, okay, or a pole pair on the j-omega axis make the system always unstable. So that's very important to remember. Okay, so now marginally stable system. So we have seen stability, we have seen instability, and next we are going to see marginally stable. So throughout this stability analysis, we are going to see the three important terms. The first term is stability. The second term is instability or instability. Third one is marginally stable. Marginally stable system. So I have explained you what is stability, or explained what is instability, and now I am going to discuss with you marginally stable system. So we see what is a marginally stable system. So if you see that marginally unstable system, marginally unstable system. So marginally unstable, marginally unstable. Okay, so marginally unstable means a marginally stable system is that system which we have defined in this way, that all the characteristic roots in the left half of the S plane, but for a simple roots on the imaginary axis. Okay, so what actually marginally stable means, if all the poles lie left half of the S plane but simple roots on the imaginary axis. Just note down the simple roots on the imaginary axis. If we just take marginally stable means, if I take this is S plane, so this is j omega axis, so also poles lie left half of the S plane. So here is one pole and here is one pole, and if one pole at origin, if one pole at origin, okay, if one pole at origin, so all poles are lying left of the S plane. If one pole at origin, so we say it's marginally, say a root on the origin. So all poles are lying left of the S plane, but one pole is lying on the origin. Okay, in that particular case we say a system is marginally stable. And second thing, a root pair on the j omega axis, a root pair, simple root pair on j omega axis, so we say system is marginally stable. So if we just see all the poles are lying left half of the S plane. All the poles are lying left half of the S plane. Here is one pole and here, and one simple pole pair, so it is lying on the imaginary axis. In this particular case we say marginally stable, marginally stable. So now we are going to mathematically we are going to derive stability of the system. So here the question is how to determine the stability. How to determine the stability? The question is here how to determine the stability. How to determine the stability? Okay, in general, the characteristic equation we have. The characteristic equation we have. So that characteristic equation can be written. Characteristic equation can be written as delta of S is equal to a naught S power n. Okay, an S power n minus 1 plus a2 S power n minus 2, so on, a n minus 1, so S a n is equal to 0, n is equal to 0. So this is the characteristic equation. So from this equation only we are going to determine the stability of the system. Okay, here I have to find two conditions. Okay, the first one is necessary condition, another one is the sufficient condition. So by applying necessary and sufficient condition, we are going to find the stability of the system. The first one is the necessary condition. So this should satisfy necessary condition. Necessary condition. What actually necessary condition will say? The necessary condition will say that a naught, you see that a naught, an is not equal to 0. Okay, an is not equal to 0, and the second thing, a naught should be greater than 0. If these two conditions satisfies, so necessary condition is satisfied. Okay, if these two conditions fails, so necessary condition, therefore necessary condition will fail, so we can't go further for the sufficient condition. Okay, next one is the sufficient condition. Next one is the sufficient condition. So we have to find the sufficient condition. So the sufficient condition can be found by Routh array formulation, forming Routh arrays formulation, Routh array formulation. So what is the Routh array formulation? Okay, we see here the Routh array formulation. The Routh array formulation is here. So we are going to see the Routh array formulation. So you know the characteristic equation, right? You know the characteristic equation. From the characteristic equation we are going to find a sufficient condition. So sufficient condition can be found by Routh array formulation. So you know that, so your characteristic equation, you know that, so S A naught S power n plus A1 S power n minus 1 plus A2 S power n minus 2 and A n minus 1 S A n is equal to 0. So this is our characteristic equation. Okay, so here these are A naught, A1, A2, An minus 1, An are the polynomial constants, polynomial constant. So we can write, we can formulate Routh array for this characteristic equation. Likewise, first you see that S power n. Okay, you write S power n. After that S power n minus 1. After that S power n minus 2. And after that S power n minus 3 and so on. So S power 1, S power 0. So you write all the S power terms in the column. Okay, then you just make a line here and write all the polynomial coefficients. Okay, all the polynomial coefficients. What are the polynomial coefficients here? Okay, so here, so S power n coefficient, what is that? A naught. Okay, then after, so after A naught, after this is a A2. Okay, then after A4, A2, A4, okay, A6 and A8, like this. So this is the even polynomial coefficients, even powers of S. Okay, the even polynomial coefficients. Here odd polynomial coefficients. So A power S minus 1 is a odd polynomial coefficients. So what are the odd polynomial coefficient? A1, A3, A5 and A7. So it will go like this, A9, like this it will go. So you just write these two rows. Okay, so even powers of S, this is the even powers of S, this is the odd powers of S. You just write like this. From this even powers of S and odd powers of S, we are going to write for all the other powers of S. So if you just see that, you have to find this row S power n minus 1 coefficients. Okay, you know S power n coefficients, you know S power n minus 1. This row of all even powers of S coefficients, you know, odd powers of coefficients, you know. So then here we have to find S power n minus 1 row of all the coefficients. We have to find. How to find? The first thing you should remember here to find. So you know how we are doing a matrix, but it's little slight difference here. So how I'm going to do it here, you just observe. First we have to take A. Okay, first take this one is a upside, I'm going to take a positive. Okay, then downside I'm going to take as a negative. Okay, how to find? So I'm going to put this one as a B1, this one as a B1. So here B1 is equal to, what is that? A1 into A2, A1 into A2. Okay, A1 into A2, right? So minus, okay, A0 minus a naught minus a naught into a3, you should divide by this term, that is a1. So you get the b1, right? To get b2, what I am going to do to get b2, okay? So to get b2, what I do to get b2, so you have to multiply this term, okay, and this term. So this is a plus, this is a minus, okay. So how will you do that? So b2 is equal to a1 into a4 minus a0 into a5 by, you divide by a1, so you will get b1. So to find the b3 value, to find the b3 value, so I want to find the b3 value. To find the b3 value, so what I do, so I am going to do like this. So again a1 into a6, b0 into a7, okay. So what is that? a0 into, sorry, a1 into a6 minus a0 into a7 by what? You are going to divide by a1, okay. That's how you got the b1, b2 and so on. You can get others. So then if you want s power n minus 3 coefficients, so I am going to call it, this one is the d1, okay. So now what is d1? What is d1 here? So d1, I am going to write d1 is equal to, so how are you going to write? So d1, I am going to find it. You just see that. So b1 and minus, okay. So here d1 is equal to b1 into a3 minus a1 into b2 by, you are going to divide by b1, okay. To find dt, what you have to do, you just multiply b1 a5 and a1 b3. This is a plus, this is a minus. So d2 is equal to, so b1 into a5 minus a1 into b3 by b1. So that's how we are going to get d2. So next, to like this s power n minus 4 also you can, so on you can find like this. Now if you find e1 here, so then the same method we can use, and finally we can find this is f1. The same method we are going to use it, we are going to find, okay. So this is a very important to understand Routh array formulation. Once you know Routh array formulation, it's a very easy, okay. So now here we just I'm going to explain this with a simple example. I'm going to explain with a simple example. So I take one example, I'm going to explain it. I take a first sheet, simple example, I'm going to use it, okay. So here s power 4, 8 s cubed, okay, 18 s square, okay, plus 16s plus 5. For the given characteristic equation, I have to find the stability, okay. So through this example, I am going to explain you sufficient condition, okay. You have to first check, okay, this is what is this one? This is called an is not equal to 0. So an is not equal to 0, it means 5 is not equal to 0. This is the necessary condition. So what is another one? A0. should be greater than 0. So it is, so 1 is greater than 0. So the two conditions satisfied, so that we can go for the sufficient condition. So I am going to explain you the sufficient condition through this example. Through example, I am going to explain you sufficient condition. Okay. So the sufficient condition, so you write the powers of s power 4, s power 4, s power 3, s power 2, s power 1, s power 0. This is the powers you have, right? What are the even powers of coefficients? Even powers of coefficients here. So this is a even power, and this is a even power, and 5 also even power, s power 0 into 5. So that is the even powers of s. So what is that? 1, next 18, and here is the 5. Okay. Next one, what are the odd powers of s cubed? So that is a 8. Okay. This is a 16, and it is a 0. Okay. It is 0. Okay. So what I am going to do here, you have to find s square coefficients. To find s square coefficients, what I do here, so you know that 1 into 18, 1 into 18, and 1 into 16. Okay. So 8 into 18 minus 1 into 16. Okay. So next, by we have to divide this with the 8. Okay. So this value you will get, if you just do this mathematical calculation, so you will get, 1 minute, so you can do mathematical equation. So this value will be how much you will get? 144 minus 16 by 80. Alright. So this is how much you will get. How much you will get this one? So 128 by 8. Okay. How much you get this one? 8. You will get this one, 20. So how much you will get here? You will get the value. So 8 into 18. 8 into 18 is equal to 144. Then 1 into 16 minus 16. So then divided by 18. So 128 by 8. So how much you will get? So that you will get 16. So you will get the 16. This is 16. So this value is 16. So you see that 8 into 18, 8 into 18 minus 1 into 16. I am going to divide it by the 18. So you will get the values here. You get the 16. So next, so 8 into 5. So 1 into 0. So next 8 into 5 minus 1 into 0 by so how much you have to divide by the 8. So this is a 40. So how much you will get? 40 divided by 8. So you will get 5. So so you will get 5. So this value will be 5. So further if we do, it will become 0. So next what you have to do, next to find the S1 coefficient, so you have to multiply these two. This is for this, this is for this, this is for this. So now we are going to find S1 power coefficients. To find that, so this one into this one, this is a minus, this one is the plus. Okay, so then what you get here, 16 into 16, okay, minus 8 into 5 divided by 16. Okay, 16 into 16, how much you get? 256 minus 40 by 16, so minus 40. So how much? 216 by 16, 216 by 16, how much you will get? So you will get, so it's around you will get right. So here, so we find that 216 divided by 16, how much you will get? 13.5. 216 divided by 16, so we get 13.5 here, 13.5. So further we do, it become 0. So again, to find S power 0 coefficient, so what we do, 13.5 into 5, okay, minus 16 into 0, okay, by 13.5. So what happened? So you will get 13.5 into 5 by 13.5 is equal to, you will get 5. Okay, this is the 5 we got. Okay, this is the Routh complete array. So this is Routh complete array. This is Routh complete array. So answer of the stability will be given by examining the coefficients of first column of the Routh array. You just see that the coefficients of first column of Routh array here. So we have examined their signs, not magnitudes. Okay, and you see that this criteria says that if there is no sign change, that all of them are positive, then we say system is stable. What I mean to say that here, if we just take this first column of all the elements, okay, all the elements should be positive, then we say the system is stable. Okay, so again, once again I'm repeating. So if first column of this elements should be positive, they should be positive, so the system is stable. So the system is stable. The system is stable. So what criteria says that if there is no sign change, that all of them are positive, then we say system is stable. So what we have observed here, see the first column of all elements are positive. In other words, the first column, when you examine this first column, there won't be any sign changes, then we say the system is stable. So when you say unstable, number of sign changes, you can write here number of sign changes is equal to number of pole lie right off of the S plane, right above the S plane. Here the location of the poles cannot be determined. Location of the poles cannot be determined. Only we say whether system is stable or unstable. Okay, so this is the first example. So I'm going to repeat here. So how we going to find stability for the system? So you just examine first column of this elements. Examine now all these coefficients of the first column of the Routh array, and you check it. If there is no sign changes, we say the system is stable. This system is stable system because there is no sign changes in the first column of the Routh array. So the system is stable. So we will see a few other examples. So we are going to find